Hello everyone. So in this video I will try to answer the questions from chapter 18, two questions, questions 4 and 5. So even though in these questions they explicitly ask you to explain in words, I thought there was some room for quantitative work, and I wanted to demonstrate how you could go about this. So in question 4 they are saying explain in words how Charles' law follows from kinetic theory and the relation between average kinetic energy and the absolute temperature. And in question 5 the same thing but for Gay-Lussac's law. Right. So Charles' law is that the volume is proportional to temperature for constant P, and Gay-Lussac's law is pressure is proportional to temperature for constant V, constant volume. Right. So let's see if we can drive this from the kinetic theory. So questions 4 and 5, and for 4 is Charles' law. And that just states V is proportional to T for constant P. And 5 is Gay-Lussac's law. And that says P is proportional to T for constant V. Okay. And they're asking us to do this through kinetic theory. So I'm going to use the technique that we actually used when we were discussing kinetic theory. I'm going to have a cubic box of side length L, and I'm going to just look at one side of this, let's say this right side, which is some area A, which is of course just L squared. Okay. And I want to show that the V is proportional to T when we keep the pressure constant. Right, so as we increase the temperature, the volume should just increase if you want to keep the pressure constant. Now the pressure is of course just the force per unit area, and let's start with this one actually. Let's start with 5. That's going to be a little bit easier conceptually, I think. So pressure is just force per unit area. Since we are keeping the volume constant, the area is not going to change. We'll just keep our whole shape the same, but we are going to change the temperature, and this is going to have some effect on the force. Now it is going to have an effect on the force twice, because this F is delta P, so m times delta V divided by delta T, right, by A. So this delta P is the momentum imparted per collision. Right, so each time our molecule hit the side of the wall, it's going to impart some momentum. It's just going to change its velocity in one direction, in one component, and this is the time between the collisions. Right? And this is of course the surface area, it's just L squared. So both of these are going to change. Let's say that I'm changing temperature. So temperature is related to velocity. As you know, mv squared is proportional to T. So let's say I change my temperature to some T prime, which is, let's say, alpha times T. Right? In this case, my V should change to some V prime, which would be just square root of alpha times V. Okay. And this is going to have an effect on this delta P and delta T. So delta P is going to get to delta P prime, which should be just square root of alpha times delta P, right? Because we are increasing, so remember what delta P is. So delta P is just m times delta V, and this is in fact m times 2Vx, something like that. Right? So if I just if I change my velocity by a factor of square root of alpha, my change in momentum should also change by the same factor. Right? And this delta T is also going to change. That delta T is going to go to some, let's say, delta T prime, and that's going to be delta T divided by square root of alpha. Right? If I increase my velocity by this factor, then it takes a shorter amount of time to come back and hit the wall again. So the time between the collisions will decrease by the same factor. Now if you put this in, if you put everything in, the pressure is going to change to some P prime, and that's going to be equal to, so the numerator doesn't change, square root of alpha delta P divided by delta T by square root of alpha divided by A, and that comes to just alpha times delta P by delta T over A, and this is going to be equal to alpha times P. So we have established Gay-Lussac's law, right? If we change the temperature by a factor of alpha, our pressure if we don't change the volume, so we keep the area constant, then and this doesn't have an effect on the delta T. The only effect on delta T comes from the change in velocity. Then the pressure is going to change by the same factor, right? So Gay-Lussac law is established. Right. Now, if you look at Charles's law, that V is proportional to T for constant P. Let me erase this, but even though I'm going to use the ideas from here, I don't think I need them in detail. That's a little bit more complicated, but the basic logic is the same. So again, let's say that my T goes to some T prime, which is just alpha times T, then my V is going to some V prime, which is square root of alpha times V, and my pressure is going to go some P prime, which is going to be equal to some delta P, the change in momentum prime, over delta T prime divided by A prime. Okay? So what we want is that, let's say that we are going to be changing our volume by some factor, right? Let's say that our let's say our length is changing by some factor. That will make things easier. So our L goes to some L prime, which is just beta times L. So in this case, our A is going to go some A prime, which is beta square A. The area is going to change as the square of beta, and the volume is going to go to some V prime, which is of course the cube of beta times our original volume. Right? So we're going to have this change, and we want to show that this in fact changes the same way that the temperature changes if the pressure is constant. So how does our pressure change as we change our temperature? And let's say that our volume is also allowed to change in this case, so we can have volume change this way, so our A and L can change. So this is going to become, so our delta P prime is still going to be square root of alpha times our delta P. So delta P prime is square root of alpha times delta P. By the same logic, if our temperature is changing by a factor of alpha, our velocity is going to change. Each collision is going to impart a little bit different momentum. Now the time between the collisions, though, delta T prime, is going to change in two ways. First, there is this factor of delta T over square root of alpha. This comes from the fact that the velocity changes, so it takes less time to travel the same distance, but it's not the same distance, right? We are allowing our distance to change here, and the longer this distance, the longer it is going to take. So the time it takes is going to be proportional to this beta. Okay? And finally, now our A is not going to be the same. Our A prime is going to be just beta square times our original A, which means that our P prime, our modified pressure in this case, is going to be square root of alpha delta P by beta delta T by square root of alpha by beta square alpha. And you can just check that this is alpha by beta cube delta P by delta T, or alpha by beta cube our original P, our original pressure. Now I know that there is some confusion here between the lowercase p, which is momentum, and uppercase p, which is pressure, but I hope you can follow the argument. Right? So we want these two to be the same, right? So we want our pressure not to change. We want constant pressure. So we require this, which then says that alpha is equal to beta cube. But then it means that our volume is changing in proportion to alpha, right? Which is how our temperature has changed. So we have also established Charles's law, right? So this is how you could go about this quantitatively. But of course, in the book they are asking to explain this by words, and well, that I think you can find elsewhere. Okay, thank you.